Hi there. So in this section, what we're going to talk about are measures of central tendency and standard deviation. Essentially, what we're looking at is the following. When you have a large data set and you want to make some sense of it, you want to ask yourself, well, what is this data set telling me? What information is this giving to me? And what type of generalizations can we make from this data set? Well, there's different ways that we can look at the data sets, and we're just going to discuss a few of them. One of them involves the measures of central tendency. Okay? Now, we think of this very often as our average. Okay? There's three measures of central tendency that we discuss. We discuss the mean, the median, and the mode. Okay? So, let's first start out with the mean. The mean is the average as we know it. So that's probably what you've had the most experience with. So when you find the mean of a data set, for example, if you want to take your class average with your test scores or something like that, what do you tend to do? You tend to add them all up and then divide by the total number. And that's exactly what we do. We add up all of our data points and then divide by the number of data points. And that gives us what we call our mean. Okay? Now, this is a very good way to look at all of your data, but there are some drawbacks with looking at your mean as well, and we're going to talk about them. Okay? Now, another measure of central tendency is your median, and your median is literally your middle value. So, how do you find your median? What you do is you order your data in increasing order, and then you literally take the middle value. Now, it turns out if you have an odd number of data points, there is a middle value, so you take the middle value. However, if you have an even number of data points, there technically is no middle value. You have two middle values, so then what you do is you take the mean of the two middle values. Okay? Now, last but not least, the other measure of central tendency that we talk about is called our mode. The mode is the most frequently occurring data point. And just a couple side comments about that. There can be more than one mode. There can be no mode. I mean, for example, if every data point appears just once, there is no mode. If all the data points, but two of them appear one time, and then each of these other ones appear, say, 3 times, then we have 2 modes. Okay? So, there's various advantages and disadvantages to each, and I'm not going to go very deep in my discussion here because I'm assuming that you've seen this before, at least in some form. But precisely the advantages for a lot of these different measures are exactly what their disadvantages are. For example, let's talk about the mean and the median, because those are our most common ones. Okay? Now, one of the great things about the mean is that it takes into account all your data values. Okay? Whereas the median, it doesn't take into account all your data values because you've ordered them and then you've just taken your middle value or the average of your middle values. But precisely that advantage of taking into account all your data values can also be a disadvantage. Okay? And I think perhaps one of the best examples I can give is, suppose you took a bunch of tests and you got a 93, you got a 97, you had an 88, you had an 85, you had a 90, and then you were sick and were not feeling well, and you got a 40 on a test. Okay? Now, in general, one would look at a student like this and say, they're a solid student, except for this, right? When there's a data point or points that lie very much outside of what's generally going on, those have a name. They're called outliers. Okay? So, for example, suppose this was a student and I wanted to take their class average. Well, what I would do is I would add up all my data points, and I'd get 493, and then I would divide that by 6, and I'd say, oh, their average is about an 82%. Okay? Is this student a B student? I mean, aside from this last test, I would say no. I mean, they're definitely a B student, a high B, low A student. Okay, so this 40 is called an outlier. It really brings the average down. I mean, for example, suppose we didn't count that point. Okay, so we just added up these other test scores and then we would divide by 5. Then their average would be a 90.6%. That's a huge difference. So, obviously, if all the scores are very low and then there's one very high score, that's an outlier that somebody would celebrate. All right, now, suppose we wanted to find the median of that data set, and we will include the 40. Okay, if we wanted to find the median, what we would do is we would order them from smallest to largest. So we've got 40, then 85, 88, 90, 93, and 97. Okay, now notice we have an even number of data points, so there is no one middle value. So we start on the outside and walk on in, and those are our 2 middle data points. And I claim if you take the average of those two, you get an 89. Okay, pretty similar to actually what we found with our mean when we didn't pay attention to the outlier. Okay, so does the median give you a full picture of what's going on? No, the mean definitely gives you the full picture. But the beauty of the median is it doesn't take into account the outliers, which can drastically move a data set either very large or very small. Okay? So each of these are really important, and they're things that you're going to see quite often. I mean, for example, if you move to a new town and you want to know, well, what's the average home price? What's the average rent? What's the average age in this town? You'll notice that it's always the median that's given. Okay? Again, why do you want to talk about the median income? Well, most people in a town could be impoverished, but then you have somebody who has a ton of money. That's going to definitely be an outlier. And so if you took the mean, that would definitely skew what the reality of that town actually is. So those are very important different terms to take. One of the things that I'm going to tell you is oftentimes we like to be organized when we have our data sets. And so, for example, you might have a data set where it's organized by the frequency. So we can just assume that they're test scores again. Maybe this isn't going to be very big or interesting. Maybe 3 people got an 83, 5 people got a 72, and 7 people got a 90. Okay? If we were wanting to find our mean and our median and our mode of that data set. Well, what's our mode? Our mode is 90, right? Because that's occurring most frequently. So we got the mode to be 90, okay? Now, to find your median, that's your middle data value, okay? Well, the first thing we would need to do is reverse these, correct? We'd have 5 people get a 72, 3 people get an 83, and 7 people get a 90. Again, you want to order them from smallest to largest. Now notice, we have a total of 15 data values here. So we know that our middle one is going to occur right here. So what we would have is that our median is an 83. Why? Because notice that the 7th and 8th data point fall right in here. Okay? Now, next, to find your mean, well, we don't want to take 72 plus 72 plus 72 5 times. Again, what we would do is we would take advantage of the fact that we are given our frequency. In other words, that tells us how many times to add the data point. So you would take 72 times 5 plus 83 times 3 plus 90 times 7 and then divide by 15. And not that we really care what this answer is, but let's find it anyway. We're going to get 82.6. Oh, cool. It's pretty darn close to our median. All right. So, one other way you might encounter this sort of data is instead of it just being the value and the frequency, another thing that we could have is we could be giving you the values in intervals. So, for example, value and frequency. Suppose we have this. Suppose 4 people scored between 60 and 69. 5 people scored between 70 and 79. 7 people scored between 80 and 89. And 3 people scored between 90 and 99. All right, well, we have a total of 19 data points, okay? Suppose we wanted to find the mean of this, okay? We can clearly say that our mode is somewhere in the 80s, but we're not exactly sure where it is. But what if we wanted to take the mean of this data? Well, we could use a similar process that we used here. However, what do we use for our test score when they're given in terms of intervals? And the answer is what you do is you take the midpoint. Okay? So, what we would do is we would say, what's the halfway point in each of these intervals? So, in here, you would take 64.5. This would be 74.5, 84.5, and then 94.5. Now, is this going to give us a very precise mean? No, but it will give us the big picture of what's going on. Now, you might ask, how did you get this middle value? Well, recall that the way you find the midpoint is you add the values and then divide by 2. Okay? So, the way we would find the mean of this data set right here is we would say it's 4 times 64.5 plus 5 times 74.5 plus 7 times 84.5 plus 3 times 94.5. And then again, we would divide that by the total frequency, which is 19. Okay? So those are the different ways that you might encounter this sort of thing. Now, the mean is probably the most common measure of central tendency that you've encountered. And that can give us quite a bit of information. Okay, the thing is, it doesn't necessarily tell us much about the data set. Okay, and I think that the best and most blatant way I can illustrate this is as follows. Okay, so the mean gives us the big picture, but I claim it doesn't tell us the whole story. For example, suppose I had 3 classes. Okay, and suppose each of my classes just had 5 students and they all took a test. Suppose in my first class, all 5 students scored a 50. Suppose in my next class, there was a 40%, a 30%, a 70, a 50, and a 60. And in my third class, I had an 85%, I had a 50%, I had a 90%, I had a 10%, and I had a 15%. Now, we can think what we want about each of these classes, but suppose this is exactly what happened, okay? And suppose I ask myself, well, let's find the class average. I claim with each one of these classes, if I computed the mean, it would be the same for each. I would have a 50. Okay? Now, in my first class, I don't think a mean can get more indicative than that. Okay? Everybody got the same score, which isn't necessarily a good score, but nonetheless, the mean is extremely indicative of what happened here. Okay? In my second class, yeah, my mean kind of tells me what's going on. Okay? The class is a little more spread out, but not too much. Whereas in my third class, it seems like either the students really knew the material or they really didn't. There's just one middle guy in there. Okay? So, what's the difference between these 3 classes? They all had the exact same average, but what differs in them is the spread of the data. And that's a really important thing to look at. I mean, when we compute the mean, one of the things we want to ask ourselves is how indicative is the mean of what's actually going on in our data set? And that's when we start talking about the variation of the data and different measures of variation that we can have. Okay? So, you're going to encounter various measures of variation. Some are more common than others, and we're just going to touch on a couple of them, okay? One very common measure that's very easy to compute is called the range. The range is just the difference between the largest and smallest data values. Okay? Doesn't give us much information about the entire data set. Really, all it does is tell us what's happening at either extreme. Okay? So, for example, the range here, well, the range is 0. Okay? Here our largest data point is 70, our smallest data point is 30. So here our range is 40. Whereas, check this out, our largest data point is 90, smallest is 10. We have a huge range of values. So that can give you some information, but suppose there's just one at either extreme and everybody else is bunched in the middle. Well, you have 2 outliers, and that's what the range looked at. It didn't look at the fact that the bulk of your data was actually pretty stable. Okay? So, what we want to do is we want to find a value that we can talk about that tells us how spread out the data is from the mean that takes into account every data point. Okay? And so, here's what we're going to do. Suppose we have a bunch of data points, x1, x2, x3, all the way up to what we're going to call x sub n. Okay? And suppose we have a mean. There's different notation for the mean, but at this point I'll just use x bar. What we want to know is if all of these are our data points, we want to know, well, how much do they differ from the mean? Okay, a reasonable thing to say is, well, why don't we take each data point, see how far away the mean is, and then take the average of that. Okay? In other words, take your first data point, subtract off your mean. Take your second data point, subtract off your mean. Take your third data point, subtract off your mean. And go on down the line. And then take your average. Well, the problem is you're going to get 0, right? Because that's exactly what the mean finds for you, is the average deviation there. Okay, now, why does that happen? Why do we get 0? Because it seems like we're talking like we're in a good direction here. The reason why is because if a data point is smaller than the mean, then what's going to happen? Then your data point minus the mean is going to be a negative number. Whereas if your data point is larger than the mean, you're going to get a positive number. And what happens when you take all these differences is the positives and negatives offset each other. So let's ask ourselves, how can we get rid of the negatives so that whatever we do to get rid of the negatives, we can undo in the end? And the answer is we can square things. Because we know if we square things, remember when you square something, you just take it and multiply it by itself, right? 5 squared is 5 times 5, okay? So we know that when we square things, in the end, what we can do is take the square root of it because that gets us back to where we started, okay? So, what's the standard operating procedure is to do exactly where our intuition was taking us. Take all your data points, subtract the mean, square each of those quantities, and then once you divide by n, you take the square root of it. Okay? Now, I need to say a fine point here. What we've done is we've just intuited what our standard deviation is. And it turns out that there's 2 ways to compute the standard deviation. It depends upon whether you're looking at a population or a sample. And this is something that you'll go into a lot more detail with in your next statistics course. But when you are looking at a sample, we say that our sample standard deviation, okay, is as follows. You take each data point minus the mean, square it, add them up, but instead of dividing by the number of data points, you subtract one from that number. Okay? Whereas if you're looking at a population, for a population standard deviation, that's when you do the same thing, but instead of dividing by one less than the number of data points, you divide by the number of data points. All right. So those are our standard deviations. And what I'd like to do now is kind of take our discussion a little bit further. One of the things that you're going to see in your online homework is that your calculator knows how to compute the standard deviation, and calculator instructions are contained in your online homework assignment. So I'll let you watch those little video clips in order to see how to use your calculator for that. Okay? But what I would like to do now is continue my discussion about the standard deviation just a little bit longer. Okay? So essentially, I just want to reiterate that when we're talking about our standard deviation, what we're asking about is how spread out is our data. Okay? We want to know how spread out it is for very many different reasons. Excuse me. Number one, if our data is extremely spread out, we can compute our mean, but it's not that indicative because our data set, if it's very spread out, is not very uniform or consistent. Whereas if our data set is a lot more closely related, in other words, the data values aren't quite so spread, what we see is that we have a very consistent and uniform data set. And therefore, what we can do is we can use our mean with some good confidence. Okay? So, when you have a small standard deviation, what that tells you is that your mean is indicative and that your data is fairly uniform and consistent. Whereas, if you have a large standard deviation, your data is much more spread. Hence, less uniform. Okay, and this sort of thing can actually be quite important to look at. Now, what I would like to say is, well, what is considered to be a large standard deviation versus a small standard deviation? And that's a very relative thing to talk about. In some scenarios, a standard deviation of 2 might be tiny, whereas in other scenarios, a standard deviation of 2 might actually be quite large. So, suppose, for example, I had 2 companies, and company 1 made batteries, and suppose the mean life was 25.5 hours, and suppose their standard deviation was 7.2 hours. Whereas suppose company 2, their mean life was 24.8 hours, but their standard deviation was 4.7 hours. Okay? Now, what can we say about these 2 companies and the sample of batteries that we looked at? What we could say is that in terms of which, on average, had a longer life expectancy, company 1's batteries lasted longer, right? They had a higher average life expectancy because 25.5 hours is clearly more than 24.8 hours. Okay, they have the higher mean, so that's the higher life expectancy. Now, suppose you were going out for a long trek and you wanted to be able to pack your batteries so that you could really count on the fact that they would live pretty close to what their average is. Okay? Which set of batteries is more uniform or consistent with respect to its lifespan? And this set is much more consistent and has a much more uniform life expectancy than this one because its standard deviation is so much less. Okay? So this, while these guys have a higher life expectancy, these guys have a more uniform or predictable life expectancy. Both of which pieces of information are extremely important to take note of. All right. Now, another use of our standard deviation is as a tool of measurement. Okay? And we kind of alluded to it here, and we're going to take that a little bit further. Okay? The standard deviation is a way to compare essentially apples and oranges. It's a way to compare different things when they are measured on different scales. Okay, so for example, suppose you're an admissions officer and you're looking at two students, okay, and you want to know who to accept. Suppose one student had an SAT score of 1500 and another student had an ACT score of 21. Who did better? I mean, how do you compare these things? They're hard to compare because they're scaled differently. So, in order to do so, what we try to do using our standard deviation is we try to standardize these results. Okay? So, in order to compare two things that are measured differently, what we do is we want to standardize these things so that we can then make comparisons. Now, how would you standardize these sorts of things so that you can compare the proverbial apples and oranges? Well, number one, you need a base value for comparison. In other words, okay, they got a score of 1500 on the SAT. Well, how did other people do? Okay, and we typically use our mean in that situation. Okay, but again, we've got to take into account how indicative is our mean. In other words, what we need is we need a ruler, essentially, to see how far away from the mean we are. And that is where we use our standard deviation. So when we start using our standard deviation as a unit of measurement, what we do is we call them z-scores. When we use this as a tool for measurement, they're called z-scores. And here's the formula. Z, that's our z-score, we say is x minus mu over sigma. So x is our specific data value. Mu is the notation we use for our mean. And finally, sigma is the notation that we use for our standard deviation. Now, a couple comments to make about this is as follows. One thing I want to point out is if your data value is greater than the mean, okay, this x is bigger than mu, then your z-score is going to be positive. Whereas if your data value is less than the mean, then your z-score is negative, right? If you're taking away something greater than what was there, you're going to have a negative number. So in terms of the sign, the positive versus negative of your z-score, all that tells you is if your data value is above your mean or below your mean. Okay? All right, so let's take a couple of examples here to play with, and then when we start talking about normal distributions, we're going to talk a lot more about the z-scores. So let's do this. Suppose you took a Spanish test and you scored a 90%, and the average in the class was an 88 with a standard deviation of 4. And suppose you took a French test, and on that test you scored an 80%, and in that class the class average was a 75 with a standard deviation of 5. Now, clearly a 90% is better than an 80%, of course, but relative to each class, so relative to each class, which is a better score? Okay, taking into account the average and the standard deviation, how spread out the scores are, which class did you score better in? Okay, well, clearly the further above the mean that you scored is going to be the better test. So let's do our Spanish test and find our z-score. What you do is you take your data value minus the mean and divide that by the standard deviation. I think you'll grant me that you get 1/2 here. So, did we do better than the average in the class? Absolutely. We were a 1/2 a standard deviation above the mean. Now let's talk about our French test. In this case, we got an 80. The average was a 75, and the standard deviation was a 5. Well, if you compute this z-score, we are an entire standard deviation above the mean. So while a 90% is better than an 80%, clearly, relative to each class, we actually did better on our French test. Okay, so another example of this is as follows. Okay, suppose in a certain town in the month of January, the average temperature is 36 degrees and the standard deviation is 10 degrees Fahrenheit. And in July in that town, the average temperature is a 74 degrees with a standard deviation of 8 degrees. What I want to know is as follows. In which month is a temperature of 55 degrees more unusual? So these z-scores can actually tell us how unusual our data value is. Now, how far away or how big or small does your z-score have to be in order to be deemed as unusual? Well, that depends upon the type of distribution that you're looking at, okay? So what I want to know is in which month, specifically in this town, would a temperature of 55 degrees be more unusual, okay? So what I'm going to do is compute my z-score for each of these. Again, for January, my data value is 55. I subtract the mean and then divide by my standard deviation, and I get 1.9. So we're almost 2 standard deviations above the mean. Okay, that's a pretty unusual temperature for sure. Now, in July, let's compute our z-score. Again, the temperature is 55, but now the average is 74 with a standard deviation of 8. So here we get negative 2.375. Now notice something. In January, my z-score was positive. That makes sense because 55 is a lot warmer than the average. In July, my z-score was negative precisely because it was less than the mean. Okay? Now, which is more unusual? Well, let's talk about that. Notice when you compute your z-score, it's x minus mu over sigma. If your data value is exactly equal to your mean, then your z-score is 0. If your data point is equal to your mean. Okay, so that's about as close to the mean as you can get. So we want to know which is further. Well, in absolute terms, negative 2.375 is further away from 0 than 1.9 is. Therefore, our answer would be in July. This was a lot more unusual. All right, so that finishes this up. We'll talk more about z-scores in our next video when we talk about normal distributions. Thank you.